The crosstabC function is one of the most powerful functions in the RCPA3 package and probably the function we use the most in the book. The required arguments are fairly simple, but there are a lot of optional arguments and plot-related arguments which allow you to do a lot with crosstabC. In this video, I'm going to focus on the function's optional arguments for conducting chi-squared tests and measuring the strength of association between two variables. I cover other uses of crosstabC, like making basic comparisons, controlled comparisons, and graphing relationships in separate videos. The crosstabC function has two required arguments. dv is set equal to the dependent variable, and iv is set equal to the independent variable. To conduct a chi-square test with crosstabC, you set the function's chisq argument equal to true. The function supports three different measures of association, which crosstabC will report if you set the Lambda, Somers, and/or Cramer's argument equal to true. If you are using the crosstabC function to make controlled comparisons, you conduct chi-square tests and measure association the same way, but the results look a little different with multiple cross-tabulations and need to be interpreted carefully. To learn how to use the crosstabC function to conduct a chi-square test and measure strength of association, let's work through some examples together. Let's use the crosstabC function to do a chi-square test of independence. I think it's good to think about the chi-square test is a sort of a follow-up to a cross-tabulation, where the cross-tabulation would show you the observed values and how the observed values of a dependent variable vary by categories of an independent variable. And after you see kind of the descriptive statistics for the distribution, you can conduct a chi-square test to assess whether the distribution of variables there's a relationship between the dependent variable and the independent variable, as opposed to just kind of the randomness of sampling producing an apparent relationship. So I think it's good to start with a cross-tabulation first, get a handle on the observed values in the table, and then apply a chi-square test to that. So I'm going to try this with the NES data set, the relationship between race and ethnicity of respondents as the dependent variable, the independent variable being region of the country, and using the weights to weight observations in the analysis. Let's give this a run and see what our responses look like. It's running out. Breaking lines here, we've got our different groups. I'm going to pause the video and quickly do labels for those dependent variables so we can see this a little bit more clearly. Okay, I've created some shorter labels for the values of the race and ethnicity variable. I'm hoping this gives us a cleaner table to discuss. Okay, much better. So we've got our table, and we could edit this further in addition to the DV labels, but let's just get a quick sense of it. So it's saying that we've got different race and ethnicity groups. The far right column shows the marginal distribution, so the overall distribution: 65% white, 11.4% black, 13.5% Hispanic, 3.9 or 4% Asian, 2% Native American, 4% multiple races. And we can see that across regions of the country, it varies somewhat from the total. I'm not going to go through all the rows, but just let's see. The black row, I think, varies possibly the most. In the Northeast, 9.89, Midwest 8.78, in the South much larger, 18.09, in the West much smaller, 13.84. You see how that compares to the overall total. So the idea of the chi-square test is to examine whether the the pattern that we observe is statistically significant or could be the product of random chance. How could it be the product of random chance? I mean, we conduct the NES is a random sample of individuals and contacted in the survey 934.6 weighted black respondents, and they had a distribution throughout the country that's shown here, but it is possible, it's plausible that it just occurred as this distribution has occurred as a result of random chance. And the reality, each region is really 11.4%, but we get some random deviation from that because of random sampling. And so the differences we observe possibly are the product of randomness and not a real relationship between region and race and ethnicity of the respondents. So this is our occasion to use the chi-squared test. And doing this in the crosstabC function, it's actually pretty easy. So there's a optional argument called chi-sq, chi-square. And it's a true-false statement by default. It's false, but if we set this to true, I'm going to break this to the next line. We set this true, the function should apply a chi-square test to the cross-tabulation we generate. So there's our cross-tabulation. Here comes our chi-square test of independence. The null hypothesis is that the variables are not related, meaning that they're independent, and the chi-square test assesses that possibility. According to the output here, our chi-square test statistics is a whopping 668.04, and the p-value of that test statistic is less than 0.05. This is a very, very small p-value. So what it's saying to us is that the differences we observe in the table, where the observed percentages and frequencies aren't simple reproductions of the marginal distribution, that is a real relationship and not the product of random chance. The probability that this is simply the product of random chance is in the billions or trillions, one in the trillions here. So we would reject that. And that's kind of what we would expect, that there is a history and a basis for these distributions and why the country is made up the way that it is. So not a surprising result, but that's kind of what I want. I mean, we kind of know what we were expecting, and that the chi-square test kind of confirms what we were expecting. And then when there is a relationship between variables, this are the type of results that we get. I want to make a brief comment on this part, df equals 15 of the chi-square test of independence results. This stands for degrees of freedom equals 15. What does that mean? That means that the chi-square test statistic is based on 15 independent data points. The degrees of freedom for the chi-square test is analogous to the n of a sample for descriptive statistics. So like when you have the n of a sample, it tells you, how many data points their descriptive statistic is based on. The statistical test, the chi-square test, isn't based on the individual responses. Instead, it's looking at the table values in a cross-tabulation. That's why I like when I looked at the percent black across the country. 9.89, 8.78, 18.09, 3.84. These are the values. So that means actually the frequencies, but the cells of the table are the data points for the chi-square test. So the chi-square test has as data points for its analysis all the cells, and there are 1, 2, 3, 4 columns, and 1, 2, 3, 4, 5, 6 rows. So it has 4 times 24, or 4 times 6 for 24 total cells. The interesting thing about it, so you would think, oh, these are you got 24 data points, but in reality, we don't have 24 independent data points, because if we were to kind of think about it, if we have, we know that the total, say, white population in the sample across the country is this 5,382. And if we're told that in the Northeast, there are 4 regions in the Northeast, the value is 993. In the Midwest, it's 1401. In the South, it's 1888. If we know the total and we know 3 of the column values, we could subtract those column values from the total and arrive at the frequency in the West. So even if we weren't given the frequency in the West, if we knew these 3 data points, that data point does not provide additional information to us. We essentially can derive it. So that value, if we have these, the Northeast, Midwest, and South values, the West values are determined. And you could say a similar thing if we went down a column. We know that the column total is 1412.46, and if we know in the Northeast the count of white, black, Hispanic, Asian, and Native American respondents, given those 5 values, if we subtracted those 5 values from the column subtotal, we could arrive at the count for multiple races. So the last of the row values doesn't supply additional information. So we sort of had 24 data points, but they're not all independent data points. Really, if we have 4 rows, 1, 2, 3, if we have 4 columns, only 1, 2, 3 of them provide independent data points. And if we have 6 rows, only 5 of them provide independent data points. So the degrees of freedom is the number of independent data points that are used to calculate the chi-square test statistic. The value is going to be equal to the number of columns minus 1. So we got 1, 2, 3, 4 columns, minus 1 is 3, multiplied by the number of rows minus 1. We've got 6 rows, so we have 5. So it'd be 3 columns times 5 rows. 3 times 5 is 15. That's where this is coming from. The chi-square test statistic, the 668.04 value, is based on 15 independent data points in the cross-tabulation. And this is useful in the chi-square test to give the comparison probability distribution. The chi-square test statistic is compared to a chi-square distribution. There are many different chi-square distributions, but for this particular comparison of this 668.04 chi-square test statistic, we would compare it to a chi-square distribution with 15 degrees of freedom. It'll give a very low probability value. And in general, the more data points that you can identify differences between expected and observed values, the larger the chi-squared value will be. So that adjustment and picking the right distribution for comparison purposes is pretty important.